Swayam Prabha. Digital India. Educated India.
Okay, students, today let's continue some new questions. Based on these questions, you can understand some more nanobio devices and you can use your existing knowledge. Let's come the new questions and their problems. So mainly again I will cover today some tutorials. Today I will cover some new problems that will be very much helpful to design some new device. For example, I think this you can remember this figure, right, when I taught you this one for sodium borohydride treatment. Today's questions, I just showing you two cyclic voltammogram, right? One just before treatment and second is the after treatment. These two cyclic voltammogram. Let's explain this systematically. Means when you observe this kind of cyclic voltammogram, then how you can explain and what is the characteristics of the sensor surface. And then second, when you observe this cyclic voltammogram, what is the characteristics of the sensor surface and how you can explain it. And this is very fundamental questions. If you can understand this, you can explain maximum the sensor surface modifications. See, here mainly we discussed the sodium borohydride treatment. But this cyclic voltammetry change is very generic. See, sodium borohydride change that I told you that it can increase the surface electrocatalytic activity, right? That you can remember. Now, see, if you have a catalyst like gold or maybe palladium, you can remember, right? If you have a gold surface or maybe you have palladium nanoparticle coated surface, suppose gold nanoparticles, or here maybe you have palladium nanoparticles. You can remember when we react this surface with sodium borohydride, so gold nanoparticle, then palladium, actually this shows the enhancement much faster, right? And also it is not only faster, also it can enhance the activity much better than gold nanoparticles. That's reasons I taught you already. I can summarize again. Because the sodium borohydride NaBH4, you can remember Na plus BH4 minus in the solution, then from here the hydrogen atom are adsorbed on the nanoparticle surface. In the case of palladium, it's very quick, and also self hydrolysis in the case of palladium nanoparticle is very slow because we need high pH, right? You can remember these things. So now let's explain that why we are getting, means discuss the reason for change of the below electrocatalytic activity with schematic diagram. This kind of questions will come. So schematic diagram is you have to explain this enhancement by the sodium borohydride and because of this hydrogen atom adsorption, and this is because again you can explain that because of surface reconstruction, or some surface strain is facing, that's why electrocatalytic activity change. Now you can see there is two cyclic voltammogram, no? So see, in this case, first you please check the first one. Here you see the oxidations, you can see here, and the second cyclic voltammogram you can see the oxidations, you can see at these positions. So let's explain this. Means when you observe these oxidations in the left side, it means you need lower oxidations potential, and your sensor surface actually is fewer for oxidation. It means it is highly catalytically active. That's why you can say that after sodium borohydride treatment, your surface, this sensor surface, highly electrocatalytically active, right? That you can say. And this surface, this one you can see your oxidations here, this is low, electrocatalytically active. So not only potential, also you have to check the current you are getting. See here current, how much enhancement you are getting. So generally this enhancement we are comparing in a fixed potential. So you have to fix any potential, then you can compare the amount of current we are getting. That is also another important point to compare the electrocatalytic activity of two different surfaces. So you have two different surfaces you can compare. So that you can explain. Now let's show you like a very basic diagram of the sensor that you can design. So based on this enhancement, you can design a biosensor. Like I think I taught you, like just you can modify the sensor surface with antibody 1, like with the primary antibody. Suppose this is just, for example, you want to detect just last class just some cancer biomarker. So this is your cancer biomarker, and secondary antibody that you can conjugate with some very nanoparticle like gold or palladium, which one you like. Then you can, this nanoparticle, now you can add the sodium borohydride, right? And these activations can help you to get very low limit of detections. So that's simple process you have to explain. The basic things that you have to understand, this cyclic voltammogram shift. Okay, now let's come the second questions that again we will discuss in this problem. Let's discuss these two. Here you can see that two problems I want to discuss. Here you can see 3 cyclic voltammogram. What is the factor for this change of the cyclic voltammogram? Suppose this is thus hydrogen peroxide oxidations we are measuring. Hydrogen peroxide oxidations we measure on a sensor surface. Suppose you have a gold nanoparticle modified sensor surface, and you got number 1, 2, 3, this different kind of cyclic voltammogram. Let's explain this one in the factor of electrocatalytic activity. So now it is very much clear, like which surface is the highest electrocatalytically active, which surface is the lowest electrocatalytically active. So number 1, I think now you can easily predict, is the highly active, and number 3 is the lowest. This is the lowest electrocatalytically active, and this one medium, moderate electrocatalytically active, because of the potential positions. These potential positions you can predict. So if I ask you that electrocatalytic activity why is changing, you have to explain that this activity it can come here because of aging. It can be possible, right? If you have one nanoparticle you are stored for the longer time in room temperature. There is different factors. That one factors can be like the just aging, another factor can be contamination. You can remember that I taught you with the help of XPS study. Also the AFM study also we have measured. So like this you can explain why you are getting number 1, number 2, number 3. You may get of the same surface. So that's why I told the packaging is very much important. So how that's how you have to store the electrode. So storing condition is really a important factor for biosensor development. This factor always you have to be careful. Otherwise you cannot make a very reliable sensor. You cannot commercialize your product. So this is very important factor. So first things you have to remember, your sensor that you are modifying, it should not react with just suppose you develop a sensor surface, you have primary antibody and you are making some, suppose you have some paper based membrane, right? On that membrane you just use some other reagent, so they should not react each other. That's I'm going to tell you. Suppose you have your secondary antibody, some conjugate, it is already conjugated, you have some other reagent, so they should be very much stable, they should not react. So one thing you can do, so you can just make the solution like secondary antibody or other reagent solution and drop on your like paper based membrane. If you want to use, then drop on that paper. Just how much you want to drop, that you have to optimize, that optimization conditions, that everything I taught you, like how much you need, that you can drop it here. Then you can lyophilize it. You may need like different membrane, like for each case you may need separate membrane, but you can make a lyophilized conditions, all the reagent you can keep. This is one thing. Another thing, maybe in area oxygen and other humidity, right? They also slowly can interact on your sensor other material. So its activity also can slowly decay, or they may start reactions because of humidity. So what you will do, if you see that if you buy like very commercially available sensor like glucometer test kit, they are actually storing in a very good inside a packet. So maybe that is inside, you can put it like in your case maybe in nitrogen environment you can, or maybe in vacuum condition, right? That you have to store. Okay, otherwise you can see this kind of change, cyclic voltammetric change, like it can decay slowly. Then whatever, suppose you already made a calibration curve, right? So that calibration curve, some current some current you got because of some concentrations, and from the unknown sample you want to predict the unknown concentrations. But if somehow you are not getting your surface stable, then you will be misguided, like how much actual concentration present, your target concentration present in the real sample you can't measure. So your sensor should not change your catalytic property. So that's a vacuum conditions or nitrogen environment you have to store, or it should not react with other interfering species like oxygen, or humidity also should not affect, that you should keep in mind. And other things, you have just all the reagents you can keep in the lyophilized conditions. Like this way you can improve the storage, like maybe long time you can keep for your sensor surface. And another thing is the temperature. You have to keep in mind, like can you store your sensor in the high temperature or not, that you have to properly investigate, you have to properly optimize, and which temperature your sensor is really active. If they are very much sensitive, suppose you make your sensor at 25 degrees Celsius and at 40 degrees Celsius your sensor actually behaves something different, then when you use this one in some rural area, maybe you don't have much like refrigerator conditions, then your sensor may not work, right? So it should not be very much sensitive with temperature. Also your protein, other protein that you are using, that should not be denatured at the high temperature, that you should keep in mind. So that all the things that I told you, that is the stability of your sensor surface, that you should keep in mind. Okay, so these things actually I just discussed because of to understand the catalytic property of the sensor surface. Now just let's come the second part. Second part of this, I just wanted to discuss that use this cyclic or voltammogram, means this cyclic voltammogram change you have to explain in the factor of charge transfer resistance, RCT. R means resistance, C means charge, T means transfer. So this is charge transfer resistance, right? So you know that charge transfer resistance, this factor is depend on how fast in sensor surface, how fast your electron actually transfer through the electrode surface. Suppose you have the reductant, it is oxidizing, releasing the electron. So how fast? So you can see the number 1, the cyclic voltammogram. Here actually electron is transferring very fast, right? That's why you are getting your oxidation speed in the negative side. So suppose this RCT1, and the second case this is RCT2, third case this is RCT3. You just measure, you observe it, right? So now you just think which one is the highest, which one is the lowest. So you can remember, like when your sensor surface is highly active, if the electron can transfer easily, it means your resistance or impedance value is very low because the electron can transfer easily, right? So it means RCT1 should be very, very low. So it is very, very low than the RCT2. So because it's shifted towards right in this cyclic voltammogram 2, it means its catalytic activity slow, electron transfer slow, so RCT will be higher. Then RCT3, it will be higher than RCT2. So that you can remember, but you have to explain in the exam like this way. So why this happen? So also you can explain like little bit like this, like you can remember, like suppose you have this sensor surface and you have some nanoparticle coated sensor and you have the antibody coated and then you have the antigen and then maybe secondary antibody. So those all the steps you can characterize by the means of cyclic voltammogram and RCT, right? So first steps only gold nanoparticle. So in this case you may get like this CV. Second step antibody, antibody coated. So you may get like this CV. Number 2. And third case, suppose after the additions of antigen or the antigen antibody. So it form the sandwich, then definitely what happened? The electrocatalytic activity slowly, but electron transfer rate will be slow because they are the protein. This protein stuff actually they are not that much highly conductive. So electron flow will be slow. That's why it can be like this. Then RCT3 will be very much high. So your electrocatalytic activity will be low and RCT value will be high. Like this way you can explain. So their cyclic voltammogram and charge transfer resistance, they are very much correlated each other. Okay. Okay. Now next point, how you can eliminate the side reactions of electrochemical biosensor. So this is very, very important factor, side reaction. What is the side reactions of a biosensor? Side reactions can be like if your electrode surface is very highly catalytically active. Suppose platinum surface is highly electrocatalytically active. So in this case, oxygen reduction will be very high. So you are using a buffer sample, you are using some real sample, but it contains oxygen. So it will show some like background current, and you may face reproducibility problem because of oxygen, because oxygen concentration may be different place to place, sample to sample. So you may not get the similar background current because of oxygen. Also because of oxygen reactions, you will see some current. So they are the side reactions, right? Also another factor, oxygen. See, you know the glucose oxidase, when glucose will react. So in that case, oxygen also can take part. It will produce the hydrogen peroxide. So these oxygen side reactions also can hamper. So that's why you have to be very much careful about this oxygen, dissolved oxygen effect in your biosensor development. That if you not get like very much reproducible data, then you have to think how you can reduce those effects. There definitely there is some solution how to reduce those effects. So as I told, like if your sensor surface is highly electrocatalytically active, So, in that case very definitely oxygen will show some effect. If you measure, so what you will do, you can measure a cyclic voltammogram on your sensor surface. Suppose you have a metal based sensor, right, surface, and you wanted to check the oxygen side effect, how oxygen is reacting on the sensor. What we will do on the sensor, in a buffer sample, let us measure a cyclic voltammogram. So, you see maybe cyclic voltammogram can be like this, it can be like this, because it is negative, it is positive. So, what you will see, at certain potential, slowly you can get some reduction current. You can see some reduction current at the negative side, just in a buffer sample, measured a cyclic voltammogram. You can see like this. So, you can see a cyclic, just reduction can start maybe from these positions. So, from here is reduction starting. This is because of dissolved oxygen. Now, you have the another sensor surface, you are measuring again cyclic voltammogram. In that case, you may get the oxygen can reduce from here very early, means here it can start the reduction. It means in that surface oxygen is highly active, because it can reduce easily. So, you may get, so if you apply in this potential, suppose for your biosensor, so oxygen will show its contribution. So, your number 2, if this is number 1 sensor surface, this is the number 2 sensor surface, so number 2 sensor surface is not good for the biosensor development because of this oxygen side effect. So, that is why if I tell you that let us decide a electrode material, that is the number 2 questions, the electrode material. So, you have to choose a certain material of the electrode that will show lower side reactions of this kind of oxygen. Okay, like this way you can select a best material. That is why you should not select a very highly electrocatalytically active surface like platinum, or not also very high non-conductive. You have to choose a moderate one, so that you can avoid those side reaction. Clear? Now, let us come applied potential, another factor. So, another factor is applied potential. See, in the first cyclic voltammogram, let us remove the second one. Okay, let us remove. As I told, cyclic voltammogram is a very important tools. You can get so many informations before development a biosensor. First, measure a cyclic voltammogram in your chemical solution. As I said, that your reduction is started from here, and you can see that here reduction is actually increasing, right. So, what you have to do, your applied potential you can select. As you can see here, oxygen reduction actually started, it means side reaction is much. Here, don't choose this potential, because there is, you may get a high background current. Then select around these positions. Also, another factor in may come. So, don't choose very high potential again, not very low, also not very high. If you apply very high, then you have to think your real sample may contain some different interfering species, like as I said, ascorbic acid or uric acid. So, this kind of interfering species, if you measure the cyclic voltammogram, as I told, this is a very important tool to get the information about your sensor. If you can oxidize, you can see the ascorbic acid can oxidize here, uric acid also can oxidize here. So, you should not apply this much high potential. So, that is why we are avoiding this much high potential during the biosensor development, and we are avoiding very much low potential, because there is some other background like oxygen, dissolved oxygen related effect. It is better, the best selected potential is, which potential you can say, is this region. So, this is called near 0, near 0. This potential is the best for any biosensor development, especially handling the real sample. So, here I am saying that this region is the best, but it depends on sensor to sensor, right? Some sensor case you may get in this position, but that is not, maybe in that case maybe you are not handling maybe serum, not maybe you are not handling the blood, maybe something else you are handling. So, in that potential, maybe in that biosensor, maybe in that potential you may get higher signal to background ratio, then you may choose. But in that case, other background, other interfering species that can increase the background current, so you have to avoid those. Okay. Now let's come the another factor, that is bovine serum albumin. See, bovine serum albumin, we are saying BSA, that is very important. You can use this for the development of the biosensor, because this, I think you can remember, once we are immobilizing the antibody and also we are adding some BSA. What is the role? BSA can bind the other non-occupied phase, they are very small molecule, biomolecule, and when you are going to add the secondary antibody that is conjugate with some level, they will not bind, because sometimes you are getting the high background current because your secondary antibody, that level, that may also can bind here, although you don't have target, but they may bind here. Although you may have less target concentration, but if they bind here, they can increase the background current, or they may increase, so you may get the false positive data. That's why if you use the BSA, they will help not to bind the other, like secondary antibody with label, they cannot bind, because after when we will add the secondary antibody and when we will wash the sensor surface, they can be washed out, and your sensor current will be, background current will be low. So, bovine serum albumin can help like this way. Okay. Now the last problem for this today's tutorial is discuss the principle of this biosensor. So, I may ask in this number 1 problem, what is the principle of this biosensor development? I taught the whole principle. You can see your secondary antibody that conjugated with some enzyme, like here GPDH, some enzyme, right? And here the secondary antibody conjugated with the enzyme is the very far from the surface, right? Here far and here very close. So, it is called proximity dependent. Proximity dependent, right? So, this is the principle of the biosensing development. In this case, what is the principle? You have to say proximity dependent. See, when GPDH, your secondary antibody is very close and you are getting this redox cycling reaction, see, very fast, and when this one far, then you are getting slow reaction. So, this is the principle, that by using close, this is very proximity dependent factor, you can develop biosensor and you can differentiate the concentration, right? Second problem, what is the principle here? See, here you don't need any extra chemicals, right? Only your DNA or aptamer, whatever, that is already conjugated with some electroactive probe, and they are highly electroactive. See, here also proximity dependent, but it is reagentless or reagent free biosensor, right? You don't need any extra reagent in this biosensor, right? Suppose this is your target toxin, your target. So, once target bind in a specific site, see, it bend, and your electroactive probe will come very close to the surface. In first case, proximity dependent, here also we are applying the proximity dependent, but in this case we don't need any extra reagent, but in the first case we need some extra reagents. So, this is also kind of a good sensor development technique. You can use proximity dependent, at the same time no reagent. What is the principle? They can actually fold, they can bind once chemical present. Chemical means some toxin means some target present. They can fold, they can come close to the surface and you will get the higher current. Then without target, like this way you can differentiate the concentration. So like this way you have to explain the principle and you can think some new biosensor design. Okay, so today's conclusion, that's why I taught you some biosensor design. Although I explained many problems like some biosensors, like how to design, like the was-free, that proximity dependent, reagent free. This is the very important tools. So this kind of problem I discussed in the tutorial. At the same time, I just asked you how to design a new biosensors. So this was-free or reagent-free technique is really important for point of care device development. Why? Because you don't need any sample handling, right? You just will drop your sample here, and it will go through the microfluidics to your sensor surface, right? And if you have some like DNA that is very specific with this target, then it will bind and it will show some signal change. Reagent free, it will be very easier, that's why. Also was free, you don't need many washing, so just drop and wait for the data. That's why these two concepts is really important for POC development. POC means point of care testing device. Okay, so today I taught this tutorial and you learn this technique again, and I just guided you to how to apply those technique for the practical applications. Okay, that's all for today's lecture. Thank you.